Hello guys, I'm back. In this video we're going to talk about not particularly circuits. We've already went over that. Didn't get very many views on it either, surprisingly. Excuse me. Now we're going to talk about charge and charge carriers, direction of current flow, a few things of this nature. Now, I drew a simple circuit. It's just basically a flashlight with one LED. Okay, I drew an LED for a reason, and I'll show you here in a little bit. But you got your battery, you got a switch, you got your connections, and you got your LED. Very simple circuit. Now we discussed that whatever leaves the battery goes through the LED, comes back, has to come back. We already discussed that. But we talked about current. But what is current and what's actually going on here? Well, actually what is moving here in one direction or another, and we'll get to that in a minute, is charge. Now what is charge? Well, charge is just electric charge is something that is in every atom. We have things we call charge carriers. They're particles that carry charge, that carries the charge. Your negative charge carrier is the electron. Your positive charge carrier is the proton in your normal atom. That's about as far as I'm going to go on that. We're not going to go into physics or anything, but just suffice it to say, they carry the charge. But charge is what actually does the work. It's the actual energy carrier that's going to deliver the carrier. Now, you're all used to charge to a certain extent. You're on a winter day, got some nice carpet in your house, got your favorite slippers on maybe. In the morning, heat's been on all night and all day. It's real cold out. Wintertime is notorious, for one thing, with the temperature being so low, already don't have much moisture. The heat on, it draws out the rest of the moisture. So on winter days, the humidity is extremely low, so the air is very dry. And you go marching across that carpet, you go to the light switch, and you go flip that light switch, and your finger kind of brushes against the little metal screw that holds the cover on, and you get a jolt. Well, we call that static electricity. Well, more importantly, it's static charge. And we just discharged your body. As you moved across that carpet, especially with slippers, especially rubber slippers, or slippers that has some sort of rubber sole, you build up a charge in your body. When you got to that light switch, you discharged through it. You created a current flow, and that little spark that made you jump and kind of hurt a little bit, and probably said a few little not so nice four-letter words sometimes. Well, that's charge, and we see it all the time. You see it in a thunderstorm. Lightning strike is a discharge of that charge between the cloud and the ground. It's a charge being moved down or up, depending on how the charge builds up. Now, what does that got to do with regular electricity? Well, it's the same thing. Inside the battery, in that battery, we have two different materials in there. And between them, we have an electrolyte. Alright, and it's a dry cell battery, so that electrolyte is basically a paste as opposed to wet cell battery like in your car, which it's a liquid. It's the only difference. But otherwise, we got those two metals and a paste or electrolyte paste. It's a chemical reaction that takes place that moves charge in that battery. The center post of the battery, this little part right here, generally is hooked to carbon. And yes, carbon is actually considered a metal. But in any case, that one actually gets stripped of electrons. It ends up being very highly positive charged. The case on the outside, which used to be zinc, now they use other metals now. But in any case, the outer case, which is connected here, is given those electrons by that electrolyte. And it gets negative charged. Now, I said on the last video I was going to talk about E, electromotive force. Well, what is electromotive force? Electromotive force is the force that moves the charge in a circuit. We call it voltage, or another name is potential difference. And it is actually the potential difference between this negative charge and this positive charge. The more charge on each one of these, the greater that potential difference is. So in the case of dry cell, nominal, we'll deal with nominal voltage is 1.5 volts. And it says so right there, and you probably can't see it. But in actuality, it's about 2.1. There's a certain amount of loss and resistance inside a battery that loses that. So, and in actuality, if I put almost zero load on this with a really good meter like a VTVM, which is running around 11 megs input impedance, or digital multimeter at 10 megs input impedance, doesn't draw too much current on this, you don't get much drop across that internal resistance. You will actually may find this thing around 1.6, maybe even 1.7 on a really fresh battery. But once you actually load it down, hook it to that LED or something, it's going to drop down around 1.5 volts. But that's how much potential difference between the charges is, or that's how much electromotive force it has. Now, in analysis with a hydraulic system, water, the electromotive force, E, or voltage potential, or electric potential, or potential difference, any of these terms are correct, is the pump pressure. It's the pressure the pump delivers to the water system. But the charge, with its charge carriers, the charge itself is actually the water that's moving through the pipes. So when I hook this thing into the circuit and I turn the switch on, the charge starts moving, because now I've connected up these two ends to a load. Now everybody just as happy as they'll get lucky, because what really happens, what's going on inside this battery, is this guy, this positive guy, wants to be neutral. This negative guy wants to be neutral. So it wants to have a current flow, so it can get neutral. Of course, the electrolyte's got in there say-so on the matter, for at least for a certain period of time anyway. Now, that brings up another issue. And that simply is, which way does it go? I mean, when I'm looking at the circuit, and I know that when I close that switch, I'm going to have a current flow, which direction does it go? And is that ever a debate? And the only reason I'm touching on this is because I know someone's going to ask one of these days. And it's not a debate I want to get into, but I'm going to tell you the both sides and let you decide. If you go into engineering, you go into well, in engineering you're going to take 1 year of physics anyway, at least. But you go into physics or anything, they're going to talk about conventional current, and they're going to say that conventional current it leaves the positive side of the battery, runs through, goes through the load, and comes back to the negative. In other words, positive to negative. If you go to a tech school, to your junior college or something of this nature, most likely, now I think a lot of them are starting to change, but back in my day, they hadn't yet. They will go and tell you it leaves the negative side of the battery and goes and flows through the load and comes back to the positive, called electron flow. All I'm here to tell you is that that blasted load can care less. They don't care. As long as it's got a current flow that can make it work, it don't care. They don't care who's right. And maybe they're both right. I don't know. I started out being in a tech school and learned it one way, and then I went as far as I could go through that, got my 2-year degree, and then headed to university and to get my engineering degree, and had to relearn. So it's kind of, it's kind of difficult. But the big thing is, I don't care which way it flows. The circuit really don't care which way it flows. But it is a debate, and I'm just going to give you both sides of the story, how they come up with this, and you can take it from there. The reality of both sides of the story. There are some out there that'll tell you something a little different. It's not the truth. And I picked an LED light for this reason. Let's look at conventional current first. And it's conventional because it's the oldest direction. Alright? Ben Franklin picked it. When we're with conventional current, we're flowing positive charge. So we leave the positive post of the battery. So in other words, we're leaving the center, this end, this nice little bump. And we flow, switch closed, we flow, and we go through the LED. Now if you notice, the LED's got an arrow on it. And if I use conventional current, I'm going with the arrow. And then it comes back to the negative side of the battery. Alright. Let's talk about a piece of wire. I told you that positive charge carriers are protons, but there's actually one other one. At least one that is abstract. Theorized. And well, alright, let's look at a wire. A wire is a piece of metal that's solid. Anything solid is in some form of crystal structure. The atoms are situated like one here and one here, and then maybe one down here and one down here. It may be in a cube, it may be in some sort of pyramid shape, or maybe in just various different shapes, but they're in a crystal. Now they vibrate, okay? The only time that they don't vibrate is at absolute zero, which is the lowest temperature you can go. At that point, they're not moving anymore. But as long as there's some temperature out there, they're vibrating a little bit. But that's it. That's all they're doing. So those in that nucleus, those little protons, are not about ready to go anywhere. So they're not going to be my charge carriers. They're stationary. They're stuck there. Their little nucleus with their little atom is vibrating a little bit, but it's not going to go anywhere. Not under at least normal circumstances. We nuke them, yeah, things will happen, but that's neither here nor there. So what is the positive charge carrier? Well, physicists calls them holes. Holes, like a hole in something. All right, and what it is, it's the lack of an electron. You know, all atoms like to be neutral, so whatever number of protons they have the same number of electrons. But if you take one away, you leave a little hole there where electron would like to be. And that makes it a positive ion, so they talk about the hole. And they talk about it's the holes that are the charge carrier, positive charge carrier, that's moving along this path to that LED, and then from there back to the other end of the battery. Well, the easiest way to see that and understand what they're talking about is I got a hole in the ground. I want to move that hole. How am I going to move the hole? Well, the easiest way to move the hole is I just dig another hole. But as I dig this hole, I take the dirt from it and put it in here until this is filled up. Now I got a new hole. But now I want to move the hole again. So I dig another hole. I take the dirt from it and put it in here. Now my hole's moved here. I went from here to here. And so forth. And just continuing. And that's basically what they're saying is happening. Except instead of dirt, electrons. Just jumping back and forth, moving that hole along. That lack of electron to each atom along that wire. Until it gets all the way back here, and then it's done its job. That's conventional current. What about the other one? Electron current. Where we leave the negative battery with our charge carrier, carrying our charge, and go around and come back. Now you notice that, it's going against the arrow. And like I say, in a tech school, they'll tell you that's the flow of the current, goes against the arrow. Well, electron current is just that. They believe that electrons kind of jump from one atom to the next because of this potential difference. Everything's happening because of the potential difference. It's there, it's pushing, it's the pressure, it's making something happen, okay? Electron will jump to one atom, leaving, yes, a hole. But another electron immediately gains in there and jumps over also, leaving some extra electrons, which then these little extra electrons, everybody's trying to get neutral, and we're just trying to move along. Well, the electrons are not exactly, it's not like I have Ralph here, electron number 1, is going to leave here and go all the way over here and come back over to here. Alright? It's more like if I had a pipe. And in that pipe I put, say, a bunch of marbles. Just fill her nice and full of marbles. Okay, now it's full. Can't get any more marbles in there. Now, I take and hook it up into a circuit. So that's my wire. Okay? And all of a sudden, when that circuit's fired up, I got marbles out here that's wanting to get in. So if I shove a marble in this way, at this end, everybody's going to shift over and a marble is going to fall out at this end. Not the same marble, though. I mean, eventually, I guess you could say, as you kept pushing more marbles in, eventually this very first one will eventually make it there. But in reality, it wouldn't actually happen. Various things are happening and various jumping arounds going on, so most likely not one electron that started this whole show ever makes it over here. There'll be another set of electrons that actually get there. But that's electron flow. Now you can choose whichever way you want. I'm not going to beat you up on it. I don't think it's worth it. Whether you take the current going this way or you take the current going this way, I don't care. All I want you to know that it's charged, it's actually moving. The other thing I want you to know is when you're working with something more than just a simple circuit and you're trying to study it and trying to visualize the current through all this circuitry like in a radio on a schematic, keep it the same. If you're picking conventional, you're going from positive to negative, fine. But keep it the same throughout the entire radio. If you're going electron, fine. Just keep it the same throughout the radio. That way you don't confuse yourself and you don't get in trouble. So, this ended up being longer than I thought it would be. Oh, by the way, symbol for an LED, little wiggly lines showing light. Actually little photons jumping out of there. Now, I have a question I'm going to give you. And this is a research question for you. If you do decide to research it and answer in the comments, justify your answer. Don't just sit here and say what you think or whatever. I mean, you can say what you think, that's fine. Just try to justify it. And I'm not going to come in the comments and tell you, ah, you're right or you're wrong. The next video, when I do on transformers or whatever video, I will answer this. It'll probably be a week. I'll give you a week to study it. Got a nice piece of wire. Doesn't matter what's solid. It can be stranded. I don't care what kind of wire it is. Just a piece of wire. My question is simply this. How does the current flow along that wire? Does it flow on the inside of the wire? Does it flow on the surface of the wire? Or does it do both? That's my question. Like I say, if you decide to answer it, just justify your answer. You know, don't just sit here and say, well, it flows through the wire. End of discussion. Or whatever. Just look up charge. You know, do a Google search on that. You'll probably find a Wikipedia thing on it or something, or some university lecture on it or something. Electric charge and conductors. That's the nice little hint I'll give you. Anyway, until the next time, thanks for watching. You guys have a good day and everything. And I think this video's been long enough. It's longer than the other video, and I didn't think it would be that long. But anyway, I'll see you on the next one. Thanks for watching.